I'm Ava.
And I'm Beth.
This is Calculus AP.
Are you ready to graph this function? I am.
How do asymptotes relate to calculus?
Limits.
For you visual people, this is a graph depiction of what a limit is. So here I drew f of x equals x squared, and I picked the x value of 2, which I'm just calling x. And you can see that as the graph approaches x from both the bottom and the top, as depicted by the arrows I drew, they're both reaching the same y value of a, or 4. That is essentially what a limit is.
X approaches the same value from the right and left. That's important to note. Now we're going to take a more algebraic approach. So the function must approach the same y value from the left and right. This is the definition of a limit. And this in algebraic terms, or just like notation, is the limit of f of x from the right equals the limit of f of x from the left. That's very important to note, so I'd write it down and put it in your notes. And for the specific example, the limit as x approaches 2 of x squared equals 4.
The first rule is what, Beth?
The numerator equals the denominator. We are talking about the degree. Just do the numerator over the denominator and simplify. Take the coefficient of that, which is your answer.
When the degree of the numerator is greater than the degree of the denominator, that means there is no horizontal asymptote.
You would not have a limit. The limit does not exist.
However, when the degree in the numerator is less than the degree in the denominator, that means the horizontal asymptote will always equal 0.
So, vertical asymptotes and limits. It can only equal infinity, negative infinity, or it does not exist. The first example, the limit as x approaches 0, x plus 2 divided by x squared. Now, when you plug in 0, you get the denominator to be 0. We can't have this. The denominator cannot be 0. So what you do is you take the limit from the left and you plug in a number like negative 0.1. And you plug that in for x. And you find out you get a positive. Now you look at the limit from the right as it approaches 0. And you plug in 0.1. And when you plug that in, you get a positive. Since they're both positive, the limit as x approaches 0 is positive infinity. For the second example, we have the same situation where when you plug in 2, you get 0 in the denominator, and we can't have this. However, the biggest difference is when we plug in a value from the left of 2, like 1.99, you get a negative. But if you plug in a value to the right of 2, like 2.01, you get a positive. And since these don't match, the limit does not exist. What? That was so confusing. If you got that, you're amazing. If you didn't, don't worry. How did I even get 0.1? I just chose the value to the right of 0. It can be any value to the right of 0, as long as it's close enough. And why did I choose 0? It's because that's where the vertical asymptote is. And for the left side, the same rule applies. Doesn't have to be negative 0.1, it just has to be close enough to 0. What does close enough mean? I would say within 0.5 of the value would be good, but that's just my opinion. And on this page, I just explain everything using math, and you all can follow that. I think the most complicated thing is the limits. They don't approach the same number even if you plug in 0.1 because you're just looking for the positive value. That's what tells you the limit is infinity.
Let's do more limits. So this is a fairly easy one, so It's the limit of x squared plus 2x plus 4 as x goes to 1. Since this function is just a normal quadratic function with no asymptotes or holes or anything like that, all we have to do is plug 1 into the function and we'll get the number 7 as our limit. So that's pretty easy. There's not a lot you have to do there. This next example, you have to do a little more work because it's a rational function. So it is going to contain asymptotes and it might contain a hole, so we have to check for that. As you can see, in the numerator it's x squared plus 3x plus 2, and we can factor that. You should always make sure to check if you can factor in a rational function. This factors into x plus 1 times x plus 2, and that cancels out the x plus 2 in the denominator. Since this factor canceled out, that's a hole. There's a hole when x is negative 2. Once that's removed, you can just plug 2 into the x plus 1 equation that's left, and you're left with 3 as your final answer. And also, you should always make sure to rewrite limit when x goes to 2 each time that you simplify the equation.
However, it is important to note that when you plug in the x value, you do not, I repeat, do not use limit notation.
Okay, so what does a hole look like on a graph? So after the x plus 2 cancels out, we're left with the function f of x equals x plus 1. And we know that there's a hole at x equals negative 2 because that would have made the original function have a 0 in the denominator, which of course cannot happen. So x plus 1 is just a straight line, but to represent the hole, I drew an open circle at x equals negative 2. And what this means is f of negative 2 does not exist. But the limit as f of x approaches negative 2 does exist, because the limit isn't worried about that x value. It's about the y value that the graph is approaching from either side of this x value, negative 2, and that does exist. There's no hole at y equals negative 2. So it's important to know that limits defy holes.
We have a limit here, and it's a little more complicated than the limits Ava was telling you about. And basically what we have here is we have to multiply by the conjugate. So we're going to multiply by the square root of h plus 4 plus 2 in the denominator and numerator. And once we do this, the 4's cancel out. And when you simplify, the h's cancel out. So after you plug in that number, you get the answer of 1/4. This might seem complicated, but when you see a square root, and then after the square root, there's an integer that is added or subtracted. Think about using a conjugate pair to help you solve this problem. And the reason why we have to use a conjugate pair for this one, if you were to plug in 0, the denominator equals 0, and you can't have this happen. Sort of similar to the last one, if you plug in 0, the denominator equals 0. We can't have this. So what you do is you gotta simplify this equation by expanding it. We use the FOIL method to do this. There are other strategies you can use to solve this problem, but we recommend you use the FOIL method. It's a good strategy to have, and we have a video about that if you're confused on it. Once you simplify, the 16's cancel out, and then you factor out an h, so the h's cancel out. Once you plug in 0, you get negative 8. You nailed it. Nice job if you were able to solve that problem. If not, I suggest you practice more and have confidence.
Complex limits? What are those? I didn't just say that. Sorry, guys. Okay, so we're talking about complex limits here, which is basically my way of saying when you have to add two limits together. So what I provided for you here is a graph for f of x and the piecewise function for j of x. And what I'm asking is, what's the limit of f of x plus j of x as x approaches 3? So when you have to add limits together or multiply them or subtract them or divide them, any of those four things, you have to make sure to find the limits of each function from the left and the right. So here I'm just finding all the limits. It's kind of tedious, but it's something you gotta do. And you want to line up the limits from the left next to each other and the limits from the right next to each other. And so what I finally get for my answers are 0 and 1 and 1 and 0. And so when you add the limit of f of x and j of x from the left side, they add up to 1. And when you add the limit from the right side of f of x and j of x, you also get 1. And so since the limits are the same from the right and left of the two functions added together, then you know that 1 is the limit. If they weren't the same, if you got 2 from the right side and 1 from the left side, then the limit would not exist.